So previously we discussed what is a derivative and we also proved the power rule. So the power rule said that if we differentiate an equation that is in the form x to the power n, then the derivative would be n times x to the power n minus 1. And we didn't look at the notations for differentiation, so today we are going to cover that. Now, before starting, let's just see again what we learned. We learned that a function f of x, can be differentiated, and the way we differentiate was we took the limit that h tends to 0 for f of x plus h minus f of x divided by h. And if you are not familiar with this, please go back and check the playlist and you will find the video on limits and differentiation. And also please watch the video where I proved the power rule. And now, after we know that what a differentiation is, you might have realized that x to the power n can be plugged into this expression, the definition of a derivative, and what you would end up with is n x to the power n minus 1. And the proof was basically a lengthy one, but as you can understand that normally when we would like to differentiate a function, we wouldn't prefer that method. So directly what we would like to do is we would like to use this formula that we have just derived, right? And there's also a notation. So instead of writing limits and writing f of x plus h and all these things, we simply use the notation of d by dx. Now let's see what the term d by dx actually means. Now, if you consider this, if you consider a normal graph, all right, let's say this is a straight line graph, and this is the y-axis, and this is the x-axis. So the gradient of this curve would be given by this change in y divided by this change in x. So you would write that gradient of the curve is change in y by change in x. And this is the gradient. So similarly, if we have a curve, let's say this is a curve, let's say this is a function. This curve would also have gradients, but the gradients would vary at different points. So for instance, at this point, the gradient would depend on the tangent's gradient. Then at this point, the gradient would be something different, which would depend on this tangent, right? So as you can see that the gradient will be changing at every point. So we have to form a function that maps the x input to its gradient. And that function is the derivative. But what we do is, instead of writing del y by del x, because as you can see that del y by del x can't be inferred from this graph because the change in y by change in x is different at every point. So we use a special notation that is d by dx. And this d by dx simply implies that you are doing the process of differentiation, all right? So if I write d by dx and I write an equation, let's say I write x to the power n, then the result would be n times x to the power n minus 1. So previously we had said that if the function was x to the power n, then to differentiate this function, we would directly put this inside this limit expression, and the limit expression would simplify and give us the output, right? But instead of writing all these things, we simplified all this scenario into a simple notation. So what we are inferring is that if we write d by dx and then inside this we write the function, it means that we are differentiating the function and the result would be the derivative of the function. So normally we see an equation in the form y is equals to, let's say, x squared plus 3x plus 5. And if someone said that you differentiate this function, what you would do is you would write d by dx and then you would write the equation over here. All right, and then we would use the power rule, which we are going to discuss a bit later. But notation wise, we would write like this. It means that we are taking this expression. And then we are differentiating this expression as per our formula. We will get to that later. But as you can see that this expression x squared plus 3x plus 5 is equivalent to y. So instead of writing x squared plus 3x plus 5, we could have written it like d dx of y, right? Because it's the same thing. Y and x squared plus 3x plus 5 are equal. So we could have written this like this. And this thing is more simplified into dy by dx. So what we did was we put the y exactly beside this d. So it's just a way of thinking that y is multiplied with d, but actually it's not. You can think of this. This is just notation wise. So if you see dy by dx, it means that this is the derivative of the function y. So you could have written that dy by dx is equivalent, this thing is equivalent to d dx of x squared plus 3x plus 5. And now, as we have discussed the notations, now let's get introduced to the power rule in a much more rigorous manner. So, for example, let's take a normal function x to the power 5. Alright? So, this x to the power 5 would be differentiated and we would write this d by dx. So, it means that we are differentiating this x to the power 5. And how would we differentiate this? So we have proved a formula that if there is a function x to the power n, and if we want to differentiate this function, then the result would be n times x to the power n minus 1. So what would happen is that the power would come to this left and the power would get reduced by 1. So in this case, the power was 5. So the 5 would come beside x, so it would be 5x, and the power would be reduced by 1, so it would be 4. So this 5x to the power 4 is the derivative of x to the power 5. So if you differentiate x to the power 5, you would get 5x to the power 4. And what does it mean? So it means that if you have a function x to the power 5, let's say the function looks something like this. Let's say this is x to the power 5 curve, and this 5x to the power 4 basically represents the equation that would map the derivative at every point. So let's say we have x is equals to 2. Alright, so this is x equals to 2, and this would be 2 to the power 5, 32. So at this x equals to 2 point, there would be a tangent in the tangent on the curve, that is this tangent, right? And obviously this tangent would have some type of gradient. And to find that gradient, what we have to do is we have to plug this 2 inside the derivative. So if we plug 5, 2 to the power 4 as per our derivative, we would get a result, and the result would basically show us the gradient of the tangent at x equals to 2. So essentially, if my function is x to the power 5, then d dx of x to the power 5 is 5x to the power 4. And this means that at every x point, the gradient of the curve would be given by 5x to the power 4. So if we want to find what is the gradient of the curve x to the power 5 at x equals to 1, it means that in the curve, when x is equals to 1, what would be the gradient of the tangent at that point? And the gradient of the tangent at a particular point in a curve is referred to as the gradient of the curve at that point. Alright, so to find this, to get the answer to this question, what we had to do is we have to plug in this x into the derivative. So if we say that 5, 1 to the power 4, and it comes out as 5, it means that at x equals to 1, the gradient of the tangent of the curve x to the power 5 is equals to 5. So if this is my x to the power 5 function and this is 1, so this is the point x equals to 1, and the gradient of the tangent would be 5. So this is basically what a derivative is. And we had just seen one of the rules of differentiation. There are more rules. There is the product rule, there is the quotient rule, and there is the chain rule, and a lot more, right? But our goal is to only look at the power rule in this video. So let's build up on that. Let's do some sums with this question. So here I have just written down some normal functions. You don't need to think about the complexity of this function. You don't need to know how this function looks. All right. What you need to do is you need to be able to apply the power rule we have discussed. So the power rule states that, let's write it again. The power rule states that if we have a function x to the power n, then if we differentiate this function, then the answer would be n x to the power n minus 1. So d dx x to the power n means n x to the power n minus 1. Alright? And one thing about the power rule is that the power rule is basically distributive. It means that in a function, if you have a lot of terms added or subtracted, you can apply the power rule individually to each of the terms. So it's only applicable when two terms are added or subtracted. So you can't apply the power rule when both the terms are multiplied or divided. So in this case, we have 2 by 3x cubed plus 2x to the power half. So we will individually apply the power rule on this expression, and then we will individually apply the power rule on this expression, and so on. So if we apply the power rule on this expression, on the first term, it would be 2 by 3 times 3. So 2 by 3 was there initially, it was present from the beginning. We just multiplied this power with 2 by 3. So it became 2 by 3 times 3. And then we have the x, but the power of x will be reduced by 1. So the power would come to be 2. And then if we go on, we have a plus from here. So we just put the plus as is. And then we're going to look at this expression, this term. This term has 2 multiplied to x to the power half. So what we will do is we will take this half and we will multiply the half with 2. And then we are going to reduce half by 1. So it's going to be 2 times half. And then you're going to reduce half by 1. So we would be subtracting 1 from half. So it would be minus half. And then you have your x squared. So the 2 will come to the left and the power will reduce by 1. And then you have plus 2, right? Now think about this. This 2 is basically 2x to the power 0, right? Because x to the power 0 means 1. So if you don't have any x expression, so it means that there is an x expression, but the power of that expression is 0. So if you differentiate this now, you would realize that it's 0 times 2 and x to the power minus 1. And this whole expression would basically evaluate to 0. So we can say that differentiating 2 is 0. So we don't have to write that. So by rule of thumb, any constant number, either it be 1, 200 or 1000, just a term with no x value or no variable with it, differentiating that expression would mean that it's 0. Alright, now let's just try to simplify this. We have the 3 over here, so let's cancel this 3 off. We have the 2, so let's cancel this, and we can simplify it to 2x squared plus half x to the power minus half minus 2x. So this is our answer. So this expression is dy by dx, because this is basically the derivative of this function y with respect to x. With respect to x means that we are differentiating the function which is in terms of x. So we are differentiating with respect to x. So one more thing to understand is that the power rule is only applicable if the d by dx, so let's say you are differentiating with respect to x. It's important that with which variable you are trying to differentiate. So if you are differentiating with respect to x, then the function has to be in terms of x. So it has to be in some form of x squared plus 3x plus 5 and so on. So it has to be a function which is in terms of x. So your ultimate goal is to look at if this thing and this expressions are following the same variable or not. So if it's something like this, if you have d by dx, and then if you have y squared plus 2y plus 3, then you can't directly differentiate. You can't write that it's 2y plus 2. This would be wrong, because this x and this y are different. So you have to understand, until and unless this y is a constant, which means it's just a number, unknown number, in that case you could do that, but we are considering this y is another variable, so it's a function. Maybe it contains an x expression or maybe it doesn't. So we can't directly do that. We have to do something else. We might have to do implicit differentiation for that, but that's for a later video. But what you have to understand is that this d by dx has a significance. This x has a significance, which means that the function you're trying to differentiate has to be in terms of x. All right. Now one thing about this d by dx is that this d by dx is often misinterpreted by a lot of students. That is, some people write that dy by, so let's just start with an example. Let's say we have a function y is equals to 5x plus 2x squared. And then some people do is that they write d by dx is 5 plus 4x. So they differentiate this and they write the notation in this format. So there is a mistake over here. It's saying that d by dx is equals to 5 plus 4x. Now, why is this wrong? The first thing is that when you write d by dx, it means that you are trying to differentiate something, but you haven't mentioned what you're differentiating. So you can't directly write d by dx is equals to 5 plus 4x, because remember, d by dx is basically an operation. We are trying to do some process with the function. So whenever let's say you want to differentiate y, which is a function of x, so you are basically doing a process on that function, and that process was, to be specific, the process was through this limit. But we don't show this while doing our calculation, because it's basically happening beneath the surface. What we are doing is we are trying to see what's happening from the surface, but on the inside, the main process that is happening is this. But we have formed a shortcut way, or you can say we have formed a formula that simplifies all the process. So we simply look from the surface what's happening. So in exams, you have to look from the surface. So that's why the notation signifies that d by dx, is an operation, and after d by dx, I would simply put an expression beside d by dx. So it means that I'm trying to put the differentiation operation on that expression. So if you write d by dx is equals to 5 plus 4x, it doesn't make any sense, because you aren't telling which expression am I differentiating. You just said that d by dx, this operation, is equals to 5 plus 4x, but it's not. So that's why the correct way would be to say that d by dx, and then you explicitly mention 5x plus 2x squared, and this is equivalent to 5 plus 4x. You could simply say that this is perfectly okay to do, because what you have done is you have said that I am doing the differentiation operation on 5x plus 2x squared, and then my result is this. So doing this operation gives me a result, and this result is 5 plus 4x. Also, another way you could have represented the same thing is, instead of writing 5x plus 2x squared, you could have simply written the equivalent expression of 5x plus 2x squared. So we know that 5x plus 2x squared is equivalent to y. So instead of writing this, we could have also written this. So I could have said that d by dx of y is equals to 5 plus 4x. And this is totally okay to do, but in general, we don't write like this in mathematics. What we do is we simply write dy by dx. We simply put this y beside d, and people understand that it means that we are differentiating y. The y equation is being differentiated, and the result is equivalent to 5 plus 4x. So hope you got an understanding of what the power rule means and the notation d by dx. So when you're going to do your sums in maths in your class, what you're going to do is you're going to use the dy by dx notation and the power rule, but it's better to understand what's happening rather than just memorizing, just committing to these expressions, right? So we have understood what the differentiation is, where does it come from, and we have also derived the formula that we have been using. And there's one more expression that people often use, and that is the function notation. So if we have a function, so instead of writing y is equals to something, instead of writing y is equals to 5x plus 2x squared, we could have written that f of x is equals to 5x plus 2x squared. And the general convention is that if you have a function represented in this form, and you don't write dy by dx. So you could have written dy by dx if the function was said in the form y is equals to something. All right, but in this case, we have a function that is in the function notation. So there is also another different notation for expressing derivatives. So let's say you are differentiating this function, and the result is 5 plus 4x. All right, but instead of writing dy by dx, what we will write is we will write f, then we write an tilde sign, which is also called prime, f prime of x, right? Sometimes it's also called complement. So we write it like this. So if you write f prime of x is equals to 5 plus 4x, it means that this expression f prime of x is the derivative of f of x. All right, and don't be confused that this is an inverse function, because inverse function is represented by this, and this is inverse. This is a totally different thing, and derivatives are represented by this prime sign f of x. All right, so you have to you can't confuse these two things. So this is the derivative of f of x. So either way, we could have discussed this. It's totally up to you which one you like. So if your question is in the form y is equals to something, use the dy by dx notation. If it's in the form f of x is equals to something, use the f prime of x notation. It's totally up to you. Or you could have also said that this is, you could have written this statement by your own, y is equals to 5x plus 2x squared. Then you could have written this as dy by dx would be 5 plus 4x. So either way, all good. And let's continue with our sum. So we did this one, and now let's just, for the sake of it, let's just write this f prime of x. All right, instead of writing y, let's write f of x. So let's say f of x is this function, and now you are asked to find the derivative of this function, or you are asked to differentiate f of x. So we are going to use the power rule again. And so what we are going to do is, the derivative is given by this expression f prime of x, and this is equivalent to 3 times x squared plus 4 by 3 times 5, which is 20 by 3 times x to the power 4 plus 12x. So this is the derivative of this f of x. And what does it mean? Again, I'm saying this means that if you have the function f of x, which is this, then this expression maps the x input to its derivative. So if this is a graph, and let's say at x equals to 1, you want to find the tangent's gradient. At x equals to 1, you want to find the gradient of the function. Then if you plug x equals to 1 in this function, you would get the gradient of this function. So f prime of x is a form, you can think of it as a formula that takes in the x coordinate and spits out the gradient of the curve at that point. So that's it. And let's do another one, and this is also quite simple. And if you had done calculus before in your O-levels, then you might find a better way to do this, which is the chain rule. But we haven't discussed the chain rule yet, and we are indulged in the power rule. So to use the power rule, you have to expand this. So this is a distinction that I wanted to make. So normally the power rule can be only applied where you have the function x to the power n in this format. All right, so you could apply the power rule like this and write n x to the power n minus 1. So this is the derivative. All right, but if you have a function inside another function, in this case you have this function, all right, and inside this you have x plus 2. So if you wrote this as 2 times x plus 2, then this wouldn't be correct. This is wrong, because there's another step you need to do, and that would be discussed when we do chain rule. But for this class, what we're going to do is, to solve this, we're going to expand this. So x plus 2 whole squared means x squared plus 4x plus 4. And this is also equivalent to y. So I can write the derivative dy by dx, which means I'm differentiating this function, and then the result would be 2x plus 4. And this is the answer. And you might see that if I expand this, all right, this right side one, 2 times x plus 2, though we did it incorrectly with an incorrect concept, you would realize that this basically is in fact similar to this. So if you expand this would be 2x plus 4. So you might say that, all right, this is totally okay to do, so why couldn't I do in that way? Why did I have to expand this? So this is basically a coincidence, because often you won't see this happening. And this happened because the power became 1 and also the derivative of the inside function is 1. So you got the same answer. But for different sums, for example, if we do something like this, let's say x squared plus 2 whole squared, and if you did the power rule normally on this, you could have written this as 2 times x squared plus 2, and this wouldn't be the accurate answer. Now if you expand this, if you expand the original function, you would and differentiate it, then you would realize the answer isn't similar to this. The answer is quite different. There is some extra part to this function. So that's why I'm saying that only the power rule can be applied when you have the functions in discrete form in x to the power n format, right? Not a function to the power another function or something like that. So that's for today. Hope you understand what the power rule is. And next we are going to discuss the product rule. Where did the product rule come from? We will try to look on that also, and then we're going to build up on that with some exercises.